A galaxy with almost no dark matter. How is that possible? It exists, and astronomers measured it directly today. Dark matter is invisible mass that holds galaxies together. This one looks almost free of it entirely. That sounds like a magic trick, not astrophysics, but the numbers and the images keep agreeing. The immediate takeaway is simple and a little shocking. Nature built at least one galaxy the hard way. And it kept the lights on anyway, somehow. On a dark image, a pale oval barely rises from black. That's NGC 1052d F2O, a ghost in a crowded neighborhood. It orbits within the NGC 1052 group, about 70 million light-years. Astronomers call it an ultra-diffuse galaxy, or UDG. That means big in size, but painfully faint per square arcsecond. Think Milky Way width, yet hundreds of times fewer stars. You could fly straight through and miss most starlight. Here is the oddity in plain words today. Its stars move too slowly for a heavy dark halo. Their random speeds look small, not beefy like typical dwarfs. Low speeds mean low gravity, which means little unseen mass. So the visible stuff almost accounts for everything. That flips the usual script for galaxies this puffy. Normally, such fluff needs a deep well of dark matter. Otherwise, newborn gas blows out and the lights go cold. F2O stayed lit with a seemingly shallow gravitational well. It is not bright, but it is coherent and bound. It holds star clusters and a smooth, diffuse stellar body. No massive central black hole dominates the energy budget either. We see a stable, slow, and startlingly light system. You can measure that lightness from the way stars jitter. Less jitter means less pull from both seen and unseen. And in F2O, the pull matches the starlight alone. Example in real terms, no jargon today, okay. Its diameter stretches several kiloparsecs, yet the stars barely hustle. Their speeds look closer to bicycle pace than freeway traffic. Bottom line, the galaxy is big but gravitationally featherweight. Galaxies usually grow inside massive cocoons of dark matter. Those halos pull gas in and shield it from feedback. Feedback is energy from stars and supernovae that kicks gas out. Without a deep halo, that kick wins and star formation stalls. So the rule of thumb is brutally simple. Puffy dwarfs need heavy halos or they evaporate into nothing. F2O looks puffy, yet the halo seems oddly anemic. That contradiction is why astronomers paid such close attention, because if many such galaxies existed, our models would wobble. Cosmology relies on dark matter to seed structure early. Remove that scaffold, and galaxies form too late and too few. This matters because small galaxies are the building blocks of giants. Get their physics wrong and the whole family tree shifts. Mechanically, there are only a few ways to cheat here. You can strip a halo after formation using tidal forces, or you can form a tidal dwarf from shredded spiral arms. Tidal dwarfs arise in collisions, where gas clumps without much dark matter. They glow briefly, feed star clusters, and sometimes remain bound for eons. Alternatively, measurement errors could mislead, especially distances and velocities. Distance sets scale, mass, and brightness, so it is crucial. Early debates argued F2O might be closer, which inflates missing mass claims. Later work pushed the distance farther and still found deficiency. Net result, the rule bends, but it does not shatter. How do you weigh something you can barely see? You watch how fast its parts move, and you infer gravity. Gravity sets the speed limit for stars inside a galaxy. Higher mass gives higher random speeds, even without ordered rotation. F2O barely rotates, so astronomers measured its jitter instead. They targeted bright star clusters sprinkled across the diffuse light. Each cluster acts like a test particle in the potential. Keck spectra split their light, revealing tiny Doppler shifts. Those shifts map line-of-sight velocities in kilometers per second. Add several clusters, and you estimate the overall velocity dispersion. Quick mental image, it is like checking pollen in a breeze. Weak wind, slow drift, strong wind, fast chaotic motion. F2's clusters drifted slowly, around 8 to 10 kilometers per second. For its size, a normal dark halo would push near 30. Later, deep exposures measured the diffuse starlight directly. That independent check landed on similarly low dispersions. Two methods, same answer, which strengthens the weird conclusion. Distance was the other critical knob for the calculation. A larger distance boosts true sizes and changes the mass. Refined distances placed F2O near the NGC 1052 group. At that range, the dynamical mass barely exceeds the stellar mass. In round numbers, they look almost the same order. That is not zero dark matter, but it is tiny. The uncertainty bars exist, yet they do not rescue a heavyweight halo, so the case rests on repeated, cross-checked, conservative measurements. So far, the lightness keeps surviving every new test. To see why this is wild, rewind to cosmic scaffolding. Dark matter forms a vast web threading the young universe. Gas falls onto those threads, cools, and lights up as stars. Halos are the knots where the web thickens and deepens. Inside a big halo, rotation curves stay flat with radius. Stars keep zipping around at roughly constant speed, far from centers. In the Milky Way, that speed sits near 200 kilometers. Visible mass alone cannot provide that steady, extended grip. That is the classic evidence for halos around bright galaxies. Even tiny dwarfs show the same imbalance, only more extreme. Their stars jitter fast compared to their little piles of light. Rule of thumb, dwarfs can carry 10 times more dark matter. Some carry hundreds of times more by dynamical estimates. That background sets expectations for anything puffy and faint. UDGS, by that logic, should be dark matter poster children. They are extended, fragile, and exposed to stellar feedback. Give them a weak halo and gas simply leaves forever. JWST disagrees loudly with that tidy expectation. Either it lost most of its halo after formation, or it never had much because of a special birth. Both channels exist in theory, inside the standard cosmological picture. So the picture is JWST is odd but not forbidden. First path, heavy halo early, then ripped by a neighbor. Tidal stripping works like a thief peeling mass from the outside. Dark matter lives mostly in the outskirts, so it goes first. Stars sit deeper, so more of them can ride out assaults. Pass near a giant elliptical and your halo gets shaved down. Repeat a few times and the halo becomes a shadow of itself. JWST lives near NGC 1052, a massive and active elliptical. That environment supplies the gravity needed for serious trimming. Simulations show dwarfs can lose most halo mass this way. Their sizes puff up while internal speeds drop to gentle values. Meanwhile, star formation fades as gas spills into the group medium. Second path, build from debris after a violent galaxy encounter. Collisions tear spiral disks, launching long, gas-rich tidal arms. Inside those arms, clumps condense and gravity binds fresh shards. Those shards can form tidal dwarf galaxies, poor in dark matter. They host bright star clusters and diffuse bodies, much like JWST. Faint streams around nearby group members hint at such past drama. Deep exposures show arcs and plumes, whispering about earlier encounters. Example in real terms, picture a flyby only tens of kiloparsecs. The small galaxy swings past and leaves part of itself behind. Its outer halo unbinds first, followed by gas and loose clusters. What remains is a big, soft core, floating lightly in space. Both paths explain slow velocities and bright clusters without exotic physics. Both fit within standard cold dark matter expectations, tested for decades. Observations will weigh subtle signatures to separate these two stories. Bottom line, you do not need new physics to get JWST. The star clusters in JWST are characters in this plot. They are unusually bright compared to clusters in similar dwarfs. Some pack several million solar masses into compact spheres. Their sizes span only a few parsecs across, remarkably tight. Bright clusters are perfect for precision velocity work at distance. They also record conditions present when the galaxy was young. High pressures and shocks tend to forge bigger, tougher clusters. Tidal encounters naturally supply both shocks and long-lasting pressure, so the clusters themselves point toward an eventful past. JWST hosts about a dozen, dotting the diffuse glow like buoys. They orbit slowly in a potential that feels almost baryonic alone. Their metal content appears modest, matching a low-mass stellar population. That chemistry supports a small star formation budget over time. It also fits a scenario where gas was pruned or exhausted. These clusters therefore anchor both the measurement and the backstory. Without them, the mass estimate would be far less certain. With them, the galaxy's lightness becomes difficult to dismiss. Common mistake is to treat bright clusters as tiny galaxies. They are test masses, not hidden wells of extra gravity. What to remember: the clusters are clues and rulers in one. Short answer: no, this does not kill dark matter. A few weird galaxies cannot overturn mountains of other evidence. Gravitational lensing maps halos across clusters, independent of starlight. Cosmic microwave background patterns demand non-baryonic matter to fit. galaxy rotation curves, and satellite dynamics all point the same way. What DF2O offers is a stress test, not a demolition. Simulations already make dark matter-deficient remnants after repeated stripping. Those remnants look puffy, star-poor, and kinematically gentle, like DF2O. Another neighbor, DF4, also appears strongly dark matter-deficient. Together, they hint at environmental processes sculpting the group. Claims of early impossibly massive galaxies faced similar drama recently. Initial masses looked huge, then spectroscopy trimmed some estimates. Many remain heavy for their era, yet not cosmology killers. Pattern to notice, anomalies sharpen models, they rarely smash them. The right move is careful measurement and side-by-side predictions. Data should be boringly consistent across methods and telescopes. Here, independent teams keep landing near the same dispersion. Future checks will map planetary nebulae and deeper starlight too. JWST can also hunt faint tidal tails around DF2's neighbors. If we spot clear streams, stripping becomes the favored path. If we catch newborn clusters in tails, debris birth wins. Either way, the physics stays inside the standard toolbox. So the takeaway is, DF2O is a clue, not a crisis. A galaxy with almost no dark matter sounded impossible. Yet here it is, weighed, cross-checked, and still strange. The universe loves edge cases because edges reveal the blueprint. DF2O likely grew through tides or from debris, not magic. That answer keeps dark matter and adds a new twist. What to remember, rare outliers can be the best teachers. If this sparked ideas, I would love to hear them. Subscribe for more deep dives and bring your best questions.